Okay, we're going over chapter 2, derivatives. So now we have a line background because I changed it last time and I'm too lazy to change it back. So let's go over the tangent problem, and this is what happens when they talk about derivatives. When they introduce derivatives. Let's find the tangent line to a curve. Well, let's define what a tangent is. Now let's take this circle here and let's go right here. What is this? Well, many people might say that it might be a chord. In reality, I would say that I mean it is a chord, but it's secant. That's what it's called. So it's a tangent. Well, a tangent is any place that just kisses the line at one point. And that's basically the definition. In a circle here, I guess it would be the thing that is perpendicular to the radius line. So the tangent. And we don't have to use a circle. We can do something like that. This would be a tangent line. This, I guess right here. This kind of looks linear, so I'm not going to do it here. Right there, that's a tangent line. It's touching it simply at one point. This is not a tangent line because it's not perpendicular. And well, I guess it is touching it at just one point, but it's not following like the curvature of the line. So a tangent is something that has the same direction of the curve that only touches it at one point. So that's the definition here. Now let's find an equation of the tangent line of a parabola. So let's take this parabola here, and let's say we want to find the tangent line at 1, 1. Well, first let's just take an arbitrary point, and this arbitrary point is going to be x comma x squared, because the function is y equals x squared, meaning that every input is just the output squared. Pretty simple, nothing too hard. So that means the slope between these two lines is defined as what? X squared minus 1, which is y2 minus y1, over x2 minus x1. So just a slope formula, pretty simple stuff. You can simplify this even further. So what I can do is I can actually, well, this is just a difference of squares as we know, so it's going to be x minus 1, x plus 1, x minus 1, cross these out, giving us x plus 1 left, which would be, I guess this tangent line here, right? No, actually not really. So x plus 1, would be, x plus 1 would be the line or the slope between any two x points. So let's try a different, or let's try a closer point here, and we'll say that this is 2, 4. Because we know that 2, 4 is another point on this line, then that means that if we plug it into here, the slope between these should be 3. Because 4 minus 1 over 2 minus 1 is just 3. So that means the slope between these 2 points are 3. Pretty simple. That means that x plus 1 gives us the slope of any equation as x approaches, or just gives the slope between any 2 points relative to this point on this graph. But guess what? X plus 1 means that this is very dependent on what x is. I mean, it's not very dependent, it is dependent. So if we do another point like 3 comma 9, then this becomes a slope of 4, which makes sense because yes, in a curve, sorry, let me plug my phone. In a curve, the rate of change does depend on the curvature of the graph. So let's try again, but instead we'll do a limit function. Here's why we'll do the limit function. I'm gonna move this over and I'm gonna erase all this stuff because those were just simple examples. So let's go back to the slope relative to the point 1 comma 1. So that means any x comma x squared, we use arbitrary values because x can be anything, and this will always just give you the distance, or not the distance, the slope between 2 points on the graph. So if it's a negative, then it'll also work. Vice versa, all we did was apply the slope formula using arbitrary values because any point on this any point obeys this relationship. So we can actually do limit as x approaches 1, which all that means is that this point this second point that we're choosing gets extremely close because, again, we're setting up a limit value. And I guess it was called the closeness theorem. I don't really remember the name. But if x is close, then f of x must also be close. That is the theorem there. So if these are really close, because x is approaching 1, what actually happens is if we use algebraic manipulation, again with the difference of squares, we get x plus 1, and the limit as x approaches 1 is 2. Well, because it's 1 plus 1. So that means the line of the graph at this point will always be 2. So that means at this point, there's a y equals 2x graph here. But y equals 2x doesn't agree with this relationship. All y equals 2x means is that at this point, there's a line. It has a slope of 2, but it doesn't touch the point. That's just the slope form. So all we do is we do the y relationship again, which is just 1 equals 2, 1 plus b, because we're just plugging in this point that we have. Use some simple algebra, we find b equals -1. So the line that touches, or the slope, or the equation, the line that touches 1, 1, or the tangent line, is just this equation here. So let's do one thing here, and it's going to be a thinking exercise. I mean, not really. Let's take a sinusoidal graph here. So I guess it would just be sine x. What happens if you go closer? So like, let's zoom in here. Okay, looks pretty normal here. Let's zoom in even further. Well, let's zoom in on this part right here. Well, let's zoom in even further. What happens is the line looks more and more like a graph. Try this for any function. Let's try a parabola here. Let's take this right side, it becomes that. Let's look even closer. It probably looks something like that. Let's look closer in this area. Looks like that. Even closer, that. So that is actually how derivatives are kind of made using the tangent problem here. We can basically transform them into a slope here. So the tangent line slope, again, in the definition, would simply be, and this will be a difficult version because we'll simplify it later. It's going to be f of x minus a, f of a over a x minus a. And this is just a slope formula, y2 minus y1. But instead they use a because that's the point we choose. So if we want to choose like the tangent line slope at 2, then all we do is replace a with 2 and x with a different value. But it's going to be limit as x approaches a, simply because we want to find another point that is really close. Because if we take like a parabola here, this will not give us accurately, actually that kind of looks a little accurate. This will not accurately give us the actual rate of change. But this will give us a lot more accurate rates of change. That's pretty cool. Now let's move on to equation number 2, which is find equation of tangent line to the hyperbola in y equals 3x. So it's another function at the point 3, 1. There's many ways you could go about this, but I'm just going to use the definition again. So f of x is going to be f of x, which is just going to be 3 minus over x. Minus f of a, which is just going to be 3 over 3 because you're just plugging 3 into here, over h. We can use algebraic manipulation. I guess we'll just times everything by 3 over 3, actually 3x over x, because I was going to do another one, but that's the same thing. So the x's cancel out here, but that gives it 3 minus 3x over h 3x, that would be. And guess what? That just becomes 9 minus 3x over h times 3x. Wait, oh, not over h, sorry. I was using different notation here. It wouldn't be h here because we haven't gotten to that yet, so I'm kind of jumping the gun a little bit. So it's going to be x minus a, and a would just be 3 here, and x minus 3. And again, it would just be x minus 3 times 3x, simply because a is just the point that we want to find, and we're finding tangent line at x equals 3. This can just be factored out into 3 negative x plus 3, or 3 times 3 minus x, and then x minus 3. This is actually the same exact, 3x. This is not the same exact thing, actually, because we're going to factor out a negative 1 on the top, giving us x minus 3 over 3x. We'll cancel these out, giving us negative 3 over 3x, which you can factor out to negative 1/3 x. So just algebraic manipulation using that definition, and once we have that right there, we're just going to curve fit it so we can find the tangent line of that graph. That's going to be negative 1/3 x plus c equals y. I guess we'll just use y to simplify things. And the point was 3 comma 1. So we're just going to do negative 1 over 3 times 3 plus c. Boom. Add 1. C equals 2. So this is just 2. And this is just y equals negative 1/3 x plus 2. And that is the slope of the tangent line at that point. You can graph both equations and see that it intersects exactly at that one point. And that's how you prove the tangent line. Velocity problem is the same thing. I'm not going to really go over it. You should know this. So average velocity is actually just a slope formula because it's the average rate of change. The reason why they don't say average slope or average rate of change, typically in algebra 1, algebra 2, is because we usually use a line. And with a line, it has the same rate of change throughout all points. But when it's a curves, we're using average rate of change simply because the delta y and delta x, the slope isn't the same at all points. Here it's the slope is here. Here the slope, sorry, that's not right. The slope would be there. Here it'd be even more steeper, and go on, so on and so forth. So yeah, that's the logic there. Now, let's get on to instantaneous velocity, which is just the same exact thing as the slope formula limit, h over 0, but they're going to apply it to a real-life velocity function. So be velocity of a plus h minus velocity of h, and v of h is just the velocity formula for each one. So it's just a function pretty much. So it's the same thing as f of a plus h. And the way they derived a plus h is because if we look at a on a number line, a plus h, this distance is h. So what happens if h gets infinitesimally close because it's approaching 0? So really close to 0. That means this is a plus h because h is getting really small. So this gap is getting really small as h is approaching 0, which is exactly what we want because we don't want the gap to be huge like this. Instead, we want the graph to be very minimally small, and that will allow us to calculate the instantaneous slope. So the derivative of a function is denoted in multiple ways, but you'll likely see f prime of a, most common one. An alternate form. And then the most common form of derivative is this. I mean, this is my favorite one. Actually, this is not my favorite one because there's a simpler one, which I would say it helps a lot of people understand. It's f of x plus delta x minus f of x over h because it's just that small change in delta x. But I don't think they wanted to repeat variables, so I guess that's the issue. Additionally, like if you're foiling it out and you have delta x, you might get confused with this x, which is also like there was a problem on my calculus textbook that had plus and h. And like I kept getting mixed, I mean, no, plus and t, and I kept getting mixed up. Super hard to FOIL. So all I did was sub in t for r, solve it, and then switch it out at the end. So I mean, that was quite, I guess, some good thinking there. The alternate form was the one I showed you before. Let's find the derivative of a function. Same thing. I'm just gonna go really simple here. X squared. So we just apply f of x plus h, which is just gonna be x plus h. Squared, which is just the same as x squared plus h squared. I'm just kidding. Minus x squared over h. That's actually a grave mistake. Never do that. You would have to apply the binomial expansion theorem. But luckily, I already know the expansion here. And then cross out the x squared, and then cross out the h's, which gives you 2x plus h. But notice that h is approaching 0, so it's going like that. Also, the reason why you can just cross out the h's here is because this is actually a function if you graph it. And if you graph it, the function will look something, I'm not going to explain what it's going to look like, but the function is going to look like something, and as h is approaching 0, that's the only part where it's not continuous because of this asymptote, so you can just cross it out because the limit as something is approaching another thing is not the same, or is not the same as the function at that point, as we know, because like if we take like a function like 1 over x minus 2, or 1 over x, let's just say, I guess there is no limit as x approaches 0 there, but it can, like, as x approaching 0 from the right side, it goes to infinity, and as we know, that's not the same as 1 over x, or 1 over 0, which is actually undefined. So, I don't know, it's a little bit difficult to explain. But yeah. Next, we'll go over the equation of the tangent line. Before we used a formula called the point slope, but we're going to simplify things. I mean, this actually complicates things, in my opinion. So we're going to get f of a equals f prime of a times x minus a. Wow, super complicated, right? No, it's not. So let's go over what the derivative is. Again, the derivative is just going to be f of x minus, or sorry, plus a. Wait, no. I guess it would be f of a. Wait, hold on. Let me do the math. Oh no, it's f of x minus f of a over x minus a. Right. Yes. So all you're doing is multiplying x minus a, so these cross out, giving you just this function, which is the change in the thing. So that's how it was derived. Point slope function. Yeah, pretty simple there. I don't know any more else to explain. Sorry, it's y minus f of a, or the same thing as f of x minus a. This is the graph here because all you're doing is crossing out the x minus a on the top and bottom, giving you that. Pretty simple. Okay, now let's find an equation of a tangent line to the parabola at this function here. Actually, I'm not even going to do it. We already know how to do it. You just FOIL it out and stuff. Rate of change is the same thing. Let's just take this graph, and this is what my teacher drew. Looks like a square root function. So let's take these 2 points here. So what is the difference in y? We're just going to denote as delta y, delta x. This is a very inaccurate slope here, but it's the average rate of change because here we're going to assume that this interval has the same rate of change as this interval. So that's why it's called the average rate of change. But instantaneous rate of change is different because once we take it here, it becomes a lot more accurate. Again, same thing as like kind of zooming into a slope. Like let's do it one more time as a thought experiment. Here's going to be a circle. A semicircle, I guess it would be. Let's zoom in a little bit closer to the top. It looks a little bit more curved. Zoom in even closer. It looks a little bit more curved. Zoom a little bit closer. Zoom a little bit closer. Zoom a little bit closer. Kind of like if you're zooming into a person more and more, and if you have an electron microscope, you can see the atoms within their face. So we're kind of seeing the building blocks, which is just, I guess, you could define it as infinite lines. So yeah, infinite small lines. So yeah. I guess that would be it. But some rates that you do have to understand, or not understand really, but keep in mind is power. So as you know, I mean, you probably don't know, but it's power equals work applied over time. So MAS over time, or I guess MAD over time. Or it doesn't even have to be MAD, it could be MVF squared. I mean, it's just physics, so I'm not even going to explain it. But power is something that is um, a rate. So rates of reactions. So I guess chemical kinetics, mass action law, that simple stuff. And the marginal cost, which I'm not too sure because I'm not an economics person. But I am a science person, so I knew the other ones. But yeah, that's pretty much it. One more thing though, when you're given a graph versus time, and like let's just say like money. If you take the slope, you're taking the change of money over change in time, and the units are just going to be money divided by time. So I guess it would be dollars divided by unit of time and whatever. So that's important when you're doing your homework. So that's it. So